comes to implementing the abstract data type, which is list in this case, and we'll define more such abstract data types as we go along in this course. For example, it could be a heap, it could be a stack, queue, it could be a graph, etc. So all of these abstract data types need to have certain API associated with them, which we have defined on the left-hand side of this screen, of this slide. And then on the right-hand side, what I have shown are certain design decisions when it comes to implementing these abstract data types. Right? So this is what we were discussing, and we allowed certain aspects and disallowed certain aspects. For example, unique elements, whether to do reallocation, etc. All of these questions start coming up. Right? So this is what we did, and with certain design decisions, we achieved certain. I mean, functionality is the same, but the complexity, both time and space, turn out to be different depending upon our design decisions. Right? So that is what we discussed yesterday, and then we wanted to have lists. So we discussed using arrays. We wanted to have it using a linked list. So that is going to be a primary goal of this discussion. And if you have list using list implemented as a linked list, right? Linking using pointers, then what are the complexities that turn out to be, right? So if you have to insert and you just have, so in case of a linked list, you maintain something called as a head pointer. So what is a linked list? It just means that you have all these elements that we had in the array, right? So in this case, the list contains only the integers 4 to 7 to 9. And these different, so I'm calling these yellow boxes as nodes. Each of these nodes have this arrow, right, which is blue arrow shown, which is going from, let's say, 4 to 2, 2 to 7, and so on. So all these arrows are essentially pointers, which are pointing to the address of the next node, which means that each node, that is the yellow box, not only contains the data, that is the integer, but also contains a pointer which points to the next node. And therefore, all these nodes can be interspersed anywhere in memory. These need not be contiguous like we have for arrays. And still you will be able to traverse through the linked list. Traverse, meaning that you are following the chain of pointers to go from one node to another. And which one is the starting node? Well, the starting node is designated by a different pointer, which we call as a special node, special pointer called as head. Right? So you start from the head of the list. In some sense, think about it like a serpent. You are entering the head or mouth of the serpent, and finally you are going to reach the tail of that linked list. In case of arrays, it was all easy because you had the starting address of the array. And the arrays were contiguous, so we just needed to know how many elements existed in the array. Right? But think about it, if the array is like a character array, if the array is I'll come to your question, Kaushik. If the array is a character array, then what we need is not only the starting point, but also the ending point, right? Which was our /0 or the sentinel value that we discussed in the last class. In a similar manner, how do we know that we have reached the end of the linked list? Well, as you can see in the example given, from 9, there is no further link. What does that mean? That in the node containing the value 9, the pointer is not pointing to any valid memory location. Now, how do we point a pointer to an invalid memory location? Well, for that, we have a designated pointer value called as null, which is also same as 0 or 0L, so to say. So that is going to be the value of the pointer for the last node, and that defines the tail of our serpent, right? Tail of our list. Where is the head stored? Or how do we reach the head pointer, as Kaushik is asking? In general, if you just have a linked list, let's say in C, then the head pointer has to be a special variable which you have, for example, int x, int star y, etc. These variables you need to have, let's say, declared inside main or globally. In a similar manner, the head pointer needs to be declared separately, and that is going to designate the head pointer at the list. In case of C++, or let's say in more modular programs, we can have this list class itself keep that head pointer. Right? The head class itself, the list class itself can contain that variable instead of keeping it, let's say, inside main, because main will just declare a variable of type list. So we'll say list L1, list L2, etc. and let that L1 and L2 internally take care of where that head node is or how that pointer is stored. So that means the head variable is going to be part of this class list. So that is what we will see soon. And if you lose track of the head, if you lose track of the head pointer, then you can't figure out where the list is. Right? So you need to know the head pointer to access the list. That is the only way to access elements inside the list. Okay. Any basic questions on this one? Unless, otherwise we'll start discussing the complexities. Yeah, so here is where we are starting the basic data structures, so to say, linked data structures. So if you have any basic questions also, please get those clarified. Later you'll feel more shy to ask questions when we go to, let's say, trees and graphs. So feel free to ask even if you have basic questions, okay? Pointers, whatever. All right. So if we are given the elements in this manner in the link, okay, there is a question. Kaushik is saying, so for every element, we need to store the value of the character along with the pointer of the next element in the list. Yes, so we need to store the value, which in this case could be a character, could be an integer, or it could be a set of items. It need not be a single value. It could be a set of items. For example, if it's a student node, you can have the name of the student, roll number of the student, you can have the faculty advisor of the hostel, etc. All of this bunched together. All of this bunched together forms one structure of the node. And that, along with that, there will be one pointer which is pointing to the next element in this list. Any other questions? So we need to have extra bits to store the pointer value as well. Yes, pointer is a separate variable, so you need extra storage for the pointer. So although I have not shown explicitly in this diagram, that arrow is essentially part of the previous node. So you need storage for the pointer. Yes. Andrea says, so will the head be stored as a static variable in the class list in CPP syntax? I'll show you quickly, just in a couple of minutes, but it is not stored as a static variable, but it is stored as a variable in the list class. So the head pointer is going to be stored in the list class, and within that, the element variable, that the element type that we have on the screen, that element should contain a pointer to the next node. In the code, I have renamed it as node rather than element, but yeah, it's the one and the same. Right? So it should not be a static variable because we want this head node to be different for different list variables. So if I have 4 to 7 to 9 and then another list of, let's say, some other numbers, the head nodes are going to be different. Right? These are two different serpents, so they have two different heads. And therefore, we should not have a static variable. We should have just a regular variable. Pavan is asked, no, I think it is. Anish is asking, is there any advantage of linked list over an array list? Good question. I will request you to hold on to it for the next slide. I have a slide actually on the comparison between arrays and linked list. But yeah, briefly, there are some advantages. For example, in the linked list, some operations become easy. If I have to insert an element in between, right? In an array, I'll have to shift the elements. Whereas in a linked list, I just need to manipulate certain pointers and I can do it actually in constant amount of time. Right? The other advantage is that you don't need contiguous storage. If you have, well, you can use arrays, but if you don't have, you can still create the data, right? Using the linked list. That's another advantage. Pavan is asking, is the head just a pointer to the first node, or is the head itself a node with the first data value? Okay. In this case, we have the head is a pointer type, which means that it is going to be of type element star. In our code, I'll show it as the node star. So it's a pointer. Head is a pointer in this case. But what you say, what Pavan is saying, that can it be the first node itself? Yes, that is also a possibility. In which case, you can always say that the invariant that the list maintains, one of the invariants, is that one element is always going to be present, or one node is always going to be present. If you consider head as the node, but if you want empty lists to be also supported, then it's probably better to have head as a pointer, which can be just a pointer. If it is null, that means that the list is empty. However, what Pavan says has an advantage, and I'll come to that as we go along. The advantage is that when you are initializing head, when you are passing it to different variables and different functions and so on, if you want to create something in the list, that is, let's say, add an element into the linked list, you will have to pass ampersand of head. That is the address of head. Why? Because if you pass it as by value, just pass function or insert of head, then you won't be able to modify head. Right? If you want head to be modified, because head might be pointing to an empty list, or head might change and so on. So that becomes a little tricky, because every time in the function you will be accessing star of head and so on, right? So that becomes a little complicated for some of us. Instead, if you always have the node, then you don't need to get into pointer of pointer. You can just work with, because that node will always exist. So ampersand of node you can pass, which is essentially the element star, rather than ampersand of head, which is going to be of type element star star. Right? So that becomes a small issue, but otherwise you can use either of these. And thankfully we are in C++, and C++ does provide pass by reference. C++ provides pass by reference, which is not supported in C. And that also is going to help us. I'll explain to you what is pass by reference soon, as we come to a code which modifies that. So don't worry about that. Any other further questions? Good. So feel free to ask these questions, no problem. Okay. So if I have to insert an element into this list, right? What is that element type? Element type is essentially that node. And within that, there is an integer and there is a pointer for now. So if I have to insert an element, maybe if I have to insert it at the end of the list, that is, if I'm inserting, let's say 5, and that is being that I want to be inserted at the end of the list, which is after 9, then I need to start from head, traverse the list, and then reach 9, and then insert the element there by creating a new node, copying the value 5, and then updating its pointer and so on. So all of this will require me to traverse through the list, and therefore the complexity of this particular operation will turn out to be order n, where n is the maximum number of elements possible in this array, in this list. Now, can this be improved? Well, there are multiple ways in which this can be improved. One of them is what I have mentioned here, that you maintain the tail, right? You maintain the tail of this list, tail of this serpent, which means that I have not only a head pointer, but also a tail pointer in my list. This is optional, but it might help you in improving the complexity of certain functions. So this is also, in some sense, a space-time trade-off, because I'm keeping an additional variable, which means that I'm requiring an additional space to reduce the complexity of the insert. Of course, the insert will become a little complicated now, because when I'm initially both head and tail will be empty. As soon as I update, as soon as I add the first element, you should update not only head but also the tail. All right, so that becomes one way in which you can achieve this order 1 complexity, because you have the tail variable available. You just add the new node there. All of that is going to take constant amount of time, and that will be helpful in order 1 time. Is there any other way in which I can achieve order 1 complexity for list insert? Pavan says doubly linked list. Sure, yes, that is one possibility. And we'll come to doubly linked lists also. Because in doubly linked list, typically you will have a tail pointer, so you can insert it there. Adarsh and Vishwa have suggested that maybe we can insert it at the beginning, because in case of, and Aniruddha also, uh, we didn't say anything about the ordering of the elements. So why do you want to really insert it after 9? Right? You could as well insert it at the start. If you insert it at the head, that means that the head will now point to a new node, which will contain that value 5, and 5 will start pointing to 4. And that is still a list from the semantics of the list that we have defined, and therefore it will still suffice, and our insert operation can become still orderable. Right? So this is again a design decision that we have to make. If you have to find an element, irrespective of how many pointers we keep, irrespective of where we insert at the start or end, we will have to require order n time, uh, even if all the elements in the list are sorted, still we will require order n time to find an element. Right? So we cannot do like random access similar to the arrays, and therefore we'll require order n time. Removal of an element will again require you to go to that element. Essentially, it involves find, and therefore it will also require order n time. Printing the list is order n data. Size of the list, how many elements exist into this list, it can be done in order n time if you don't maintain that information. Alternatively, you can keep that information maintained in a variable called size inside this list class, and that can give you order 1 computation for the size function. Any questions on this part? Saicharan is asking, for random insertion, can we have an array holding pointers to elements? Yes, you can have. So, okay, so that's an interesting question. Now we are changing the data structure. So you have this list, and then Saicharan is asking that can we maintain an array, right, which is containing pointers to, may not be all the elements, but maybe at some elements. I mean, even you can have it all for all the elements, right? And if you have these pointers, can you improve the complexity of searching? Right? You should not require order n time. So any suggestions on, will the complexity reduce, or will it remain the same, or will it increase? So you have a list, and you also have an array pointing to the individual elements of this list. Any suggestions? Namisha says it will remain the same. Ashwin says you have to move the elements of the array. Rohit says we'll still have to travel through the array. Saicharan says it should improve. Right. Aniruddha says it will be like list using array. Saicharan says we can do binary search now. Kaushik says space complexity is high. Okay, so there are large number of reactions to Saicharan's suggestion. Right. So let's try to understand what he's saying. So Namisha says it's just using two arrays. List without address is array. Yeah. So okay, let's come to this part. So you have, if you are storing just integers, right, inside the array, inside this list, then having those additional array of pointers doesn't make sense. But if you have a larger amount of data, right, so like we said that the it could be, the node could contain, let's say, student information. It can be a large amount of data. In that case, maintaining a separate pointer can make sense. That is actually called as an index. Right? And there are reasons why that is called as an index, but essentially you are indexing into the list. So the actual data is there in the linked list. The array contains only the indices, only the pointers to individual elements. Now, the reason why Saicharan is thinking about this approach is to improve the complexity of find. So what can you do? You can find out the middle element of this array. Right? Go there and find out in the list that it is pointing to, the middle pointer is pointing to, what is the value. If that value is larger than your value that you want to search, then you know that it is in the first half, otherwise it is in the second half. Again, you do a binary search within the first half or the second half, and you go to appropriate element in this list. Right? And that way, you will be able to do a binary search onto this. Um, yeah, so why store pointers and not element itself? If the element is smaller, then you can store it directly in the array. But if the element is larger, you might still want to keep it in the linked list. You can create an array, because I was just coming to that part, that if you have the array of pointers and you have a linked list of, let's say, data, essentially this list doesn't need those pointers to be there. Right? This list doesn't need those pointers connecting each other, because you have those accessible from the index. And if that is the case, then you can as well combine the node with the pointer which you have in the array, which essentially is going to give you an array based representation, right? And then you can actually get rid of that pointer, right? So you might not gain too much by this, but this thought was very good, that to improve the complexity of find on a list, can I maintain an additional data structure which will give me an advantage, right? So this thought might be very helpful, because as I was mentioning a few minutes ago, you need not maintain a pointer to all the elements. The index can actually maintain information about, let's say, some elements. Let's say if you have millions of elements, you can still contain, let's say, 100 element array, and then 100 pointers pointing at different positions into this. Right? That can still help your search in finding the element much faster. As far as space complexity is concerned, the complexity doesn't change. It will still remain order of n, just that it will become now probably twice or a small multiple of this n. But the amount of space definitely increases. So that is one thing. But yeah, this was a very good thought, Saicharan, and I encourage all of you to keep your minds open. Think about all possible different creative solutions in improving the complexities of different operations. If it so happens, and then there was another concern here, right? So that Ashwin was suggesting that you would have to move the elements of the array. That is correct. So find is becoming faster, but the insertion will require you to move the pointers further if you want to maintain pointers to every element of this list. So that becomes kind of little, I mean, the insertion becomes a little, let's say, expensive in absolute terms. The complexity will still remain the same, because insertion in linked list is also order n, assuming that you are not maintaining that tail pointer and all. But if you are if your complexity of insert was order 1, then you should rethink about this operation. The second aspect is how many operations are there of different types. If the insertion is going to be one time, and then you are just going to populate the list, and then lots of find operations are going to happen, it might be better to optimize the find operation, right? And such an approach might turn out to be very interesting. Okay, Aniruddha says Python list is implemented similar to this array of pointers. I don't know about that, Aniruddha. Does anybody know if Python list is implemented in this manner? Okay, I think we'll have to look up online to get the answer to this. I'm not sure how it is implemented internally. But I used to feel that it is probably a map rather than a list. The reason being that you can have the index to be something else, need not be always an integer. Right? So that's the reason why I thought it to be that way, but I'm not sure. Okay, Santosh Sriram is suggesting, isn't Python list an array? I mean, it looks like an array, but I think the internal implementation might be requiring some sort of pointers. Okay, Kaushik is suggesting we can break down the entire data while doing find by storing just few address values of the linked list. So we would then need to search in a small part of the linked list only. Is this what you were telling as an advantage? Uh, yes, so the pointer array that we were separately storing, that need not store pointers to every element. We can have partitions of different elements. So there are two ways in which these partitions could be. One is you still maintain that full list, linked list, and then point to, let's say, first element, 100th element, 200th element, and so on. The alternative is you keep, let's say, 100 elements together as an array and have a pointer to that. Then another set of 100 elements together, have a pointer to that, and so on. That is also another way in which that can be done. Aniruddha has said, I had heard that Python list is not as efficient as a C array. So we had to use something like NumPy array. So I had this doubt, have to look up internet for implementation. Sure. Yes, that is, well, yeah, I have also heard actually similar thing that Python list is not as efficient as the C array, but it could be because of other reasons. It could be because maybe it is internally implemented as an online as an array, but because of reallocations, it might copy and then do it very similar to the vectors in C++. Python list is implemented using dynamic array, right? So that's what we were thinking about, as Tanay has confirmed that it's actually like a vector. So good, thanks for that. Srivatsa said Python list is a dynamic array. It also uses another array to store addresses of elements. So insertion, etc., becomes order 1. I see. Okay. Mamisha says, so similarly, we can have the first element storing the address of mid element as well. If we use a doubly linked list, then we can traverse from mid element as well. That is correct. That is possible. In fact, yeah, there is a very interesting thought that Naimisha has suggested. If the first element maintains not only the, I mean, the first pointer not only maintains the first element's address, but also the mid element's address, then we can actually decide which way to search, right? First half or the second half. But then it shouldn't stop there. We have to further maintain additional information to go to the 1/4 of that list and so on. And if you actually expand this up, or let's say, I would say, elongate this up, what you will get is essentially a tree, right? A binary tree, in fact. And if you maintain all those pointers, I'll come to that when we come to trees. But yeah, thanks for that thought. Ashwin says, Aniruddha, I think NumPy is preferred because of the interpreter overhead when Python parses loops. Yeah, I would agree with that. Surya Narayan Venkat Narayan says we can extend Naimisha's argument to other elements. Yes, exactly. And that will lead to a binary tree. Okay, great. I'm very happy with the discussion. And I think there are lots of interesting thoughts about the implementation. And again, like you had this thought about, Aniruddha had this thought about what happens in Python list. Feel free to ask that. I mean, if I don't know the answer, I think some of you will definitely find out the answer. Anish, can you repeat how insert with tail pointer is order 1? Right. So we are actually, I just. So I can maintain a tail pointer here, right? And then if I have to insert some element at the end, so let's say number 5, then I can say that 9's node dot next is going to be a new node, right, which I'll create. That new node will have value 5, and the next pointer of that new node is going to be null, and 9.next is going to be pointing to that new node, right? So and tail equal to then new node. So that tail will now start pointing to the next node. So the number of operations that we did was just a fixed constant. We don't need to traverse the list at all, and therefore the complexity becomes order. Does that seem reasonable, Anish? That is insert at the end. Sorry, Saicharan, go ahead.
Can you repeat that?
Yeah, so the tail pointer is pointing to this 9 currently, and I want to insert 5 here. So I have, let's say, created a node here. 9 will start now pointing to this, because I have the tail pointer, I can make that 9 point to the new node. New node can be created in constant amount of time, assuming that the complexity of new or malloc is order 1, although technically it should not be, but yeah, we'll assume that. And then tail pointer needs to start pointing to the new node. So that all these operations are essentially order 1. Anish is asking, that is insert at the end only or any position? No, only insert at the head or tail, or any constant number of elements away from the head and tail will be possible to be done in order 1 time. But since, and we can afford that because list is an unordered set of elements, right? So therefore we cannot insert it at any position in order 1 time. If it is like you want to maintain a sorted order, then you will require order n complexity, unless you are keeping track of it as an array, the way Saicharan has suggested. Right? Okay. Kaushik is asking, I think we do not need to preserve the order of elements, so we can insert anywhere we need. Yes. Any other concerns, questions? All right. So, yeah, this question came up, right? Why use linked lists? Right? So, I was trying to explain that. So, I'll just go over these arguments again. So, we need to copy the existing array when we do the reallocation. Right? So, like we were just discussing, inserting into this pointers array will require us to shift, but that array should have enough storage. Right? What happens essentially with these vectors, right, which we call as dynamic arrays. So, we need to reallocate memory. So, if I have 100 elements, space for 100 elements, and I have inserted all the 100 elements. For 101th element, I don't have space. So I cannot just insert it. I need to create a larger array, let's say 200 elements, copy these 100 elements to 200 element array, and then insert 101st element. And I still have space for 99 elements. So this reallocation and copying is costly. And that's sometimes the reason why you might encounter that if you write the code in C++ vectors, it gets written pretty fast. But the time that it takes might turn out to be larger than when you use C arrays. So this could be one of the reasons, and therefore you should be a little careful with, especially when you are talking about absolute performance. You can initialize the vector size, giving it some hint that I'm going to probably require 1,000,000 elements. So initialize it with 1,000,000 elements so that it doesn't do a reallocation. It has enough space already. Okay, in case of linked list, of course, that it can be done in order 1 time. Removal of an element might also require element shifting if you don't allow holes to be inside the array. Whereas in case of linked list, if you are given the pointers, then removal becomes order 1. If you are not given pointers, then you have to search for that element, and then it will still require order n time. Similar thing happens with insertion in both the cases, right, where you need to shift the elements and so on, assuming that you are inserting at the somewhere in the middle. In case of arrays, even if you insert at the start, it is going to result in order n complexity. And finally, array concatenation. If you are given 2 arrays, those can be concatenated in some sense. That is a merging, right? So we were discussing about merging for sorted arrays. Here, array concatenation is arbitrary arrays because we are talking about lists. Whereas it can be done in order 1 time if you are maintaining the tail of the list. So you just make list 1, list 2, and list 1's tail starts pointing to the head of the list 2. And that becomes essentially a concatenation of 2 lists. Shreya is asking, why can't we use vectors then? They are dynamic only, right? Again, it's exactly similar to what is the first kind of argument against the arrays, right? Dynamic arrays are having again a fixed storage. So initially you always have a fixed storage. It's just that you don't figure out that internally that reallocation is happening. So as soon as you finish the memory for the array, it is going to internally reallocate larger storage, copy the elements, and then insert the next element. So this is going to be costly. This copying business, and this copying can happen multiple number of times. as you increase the vector size. So although it is all hidden, this is called as abstraction in some sense. It is data hiding. It is hiding the implementation aspects, and therefore it is a little dangerous when you are worried about performance. So you should be aware that this is what is going to happen. There are ways in which we can circumvent this by providing a hint on the number of elements that it might have, or reserving space. There is a reserve function using which you can reserve space for a certain number of elements. Once you do that, then it becomes fine. Mani is asking, dynamic arrays and ADT? Yes, all these vectors, sets, all these STL types, all of these are abstract data types. Good point. And in fact, you don't even know how it is internally implemented, right? Whether it is implemented as a linked list, whether it is implemented as an array, and so on. You are not aware based on the functionality. That is the power of ADT. Right? And they can change it. A newer version of GCC might come up with a different implementation of dynamic arrays or vectors. Right? And your code doesn't need to change. The user program doesn't need to change. That's the interesting part. Any other concerns? All right. So it's time now to look into the code. So let me open up the code. Okay. I hope, yeah, it's visible. So we are aware of C. So I'm going to assume that we know about C, and then some of the aspects of C++ is what I need to explain. So we have stdio.h as the hash include. stdlib.h might also be required for some functions, maybe malloc or something. But then for C++, there is this IO stream which we might require. Right? That essentially has certain input-output related functions like C in, C out. Alternatively, you can stick to printf as scanf. That is also okay. It's just that to get rid of %d, %c, it becomes much easier if you use C in and C out. Okay. Although I have used both of these in different places, but yeah, you should be able to learn it pretty quickly. Okay. Then there is a data type which I am defining as a type def, which essentially is this element which is present inside each node. On the slides, I had this 4, 2, 3, etc., which were integers. Now I am defining to be a character, but you can change it, but accordingly you will have to also change some other places. But yeah, that should be the element type. Then I have a class called node. Don't worry about that class keyword. It just means that it's a structure where I can have both the elements as well as the functions which are corresponding to those elements. So it's very similar to the structure with the default access being private. So I need to mark everything as public. So what I have there is the val, which is of type data type. What is data type? That is our char. That means val is a character, and then there is a NodeStarNext, which is the pointer to the next element. Right. So this is what we were discussing. There are these two aspects which need to be, these two variables which should be present inside the node. None of these is static. And then I also have a function. I am allowed to write functions inside C++ structures as well as classes. And what it does is just prints the value. Right? That is a simple function which I'll use when I'm defining the list. Then I have a list class, which is again, this is called as encapsulation. I'm encapsulating whatever are related things together, both the variables and the methods or the functions. And that process is called as encapsulation. I mean, like we take the capsules, right, the medicine. Within that, there is multiple kinds of medicines which are capsulated or encapsulated. So this is also called as encapsulation of data and methods which are related together. Within that, I have something public and then something private. These are keywords in C++. Public means that these methods and this data, if I declare some variable here, let's say int x, that x is going to be accessible from all over the place, like global variables in C. In contrast, the private variable is not going to be accessible from outside world. So C++ provides these guarantees, which are useful for us to maintain some information only accessible to certain methods or certain functions, right? For example, if I make this public, then people might start using that variable. And then I cannot change the underlying implementation easily, seamlessly. But if I keep it private, then I'm guaranteed that nobody else is using that variable because they cannot use. The compiler is going to give you an error if you start using a private variable outside this class. So that head is essentially private to this list class. Okay, and you can make everything public for now. It's all right. You can just replace this class with struct and still the exact same code should work. Okay, what are the functions inside this class list? Like for class node, I had the print function. Similarly, for this list, I'm going to have this print function, print recursive. Those are some auxiliary functions which I have. Then size, insert, everything that we discussed about in the context of the edit. So what I have, this public interface, this part is essentially the abstract data type list. Okay. So it has insert, remove. As you can see, the removal, the find function needs to return the boolean. Like we have made a mistake on the slide that the find should not return void. Then find recursive, reverse a list, reverse recursively, and so on. So there are some functions which we have defined, and we are going to see the implementation of all of these. But there is a special function in this, which is the list name itself, right? So the name of the class is same as the name of this function inside this class, that is called as a constructor. And what is a constructor? It's a special function which gets automatically called. You don't need to call it explicitly. Like I'm going to say list L1 and then L1 dot print or L1 dot insert 5 or something like that, right? So that I don't need to call this constructor. As soon as I say list L1, this function by the name, class name, is going to get automatically called. That is called as a constructor, and that's very useful for initializing the variables. For example, I have defined node head. In case of C, I would have said node head and then head equals to null. This initialization of head is going to be very important for the overall correct functionality. So such initializations can be very nicely done, or some bookkeeping or some setting up of data structure can be nicely done using constructor. So that can be done inside the list function, that is the constructor. Okay. Constructor can also have arguments like functions. In this case, it has 0 arguments. And we'll learn all of this as we go along. This is the bare minimum that you need to know. There are other, there are some functions, some small C++ basic codes which I have made available on the course webpage. Please go through that. And if you have any questions, either ask me or post on the group. We'll be able to help. Right? All right. So that is the bare minimum that you need to know about C++. Any questions on this part about the class list declaration? Is it because list is written at the top that is default function? No, no, no. You can move it anywhere, not a problem. You can move it here also. Just that you have to keep it public. Otherwise, you won't be able to create a variable of that type. It can be anywhere. That ordering of functions doesn't matter. Any other concerns? Sure. I mean, you can have this private clause also here. Doesn't matter. It's perfectly fine. No issues. The ordering is... what is NodeStarNext in node class? In NodeStarNext is essentially the pointer to the next node. Like if this would have been C, the way I would have written this is that struct node, right? And then let's say char val and struct node star next, right? So this is what I would have defined in case of C. So in this case, next is a pointer to a structure of the same type, which we will use to point to the next element. Right? It can point to any arbitrary element, just that we will use it to point to the next element. So the same thing in C++, you don't need that struct. you can just write node star and that will suffice here. If you prefer, you can write class node star next, that is also okay. Pavan is asking a silly question. Is node star variable name same as node star variable name? Do both of these pointers point towards the node class? Yeah. So whether it should be like this or this, and does that cause a problem? No, it doesn't cause a problem. It essentially means, the reason why I write it this way is because I can define x here. Now what will be the value of type of x? Will it be node star or no? Right. So to distinguish that, I type it, yeah, correct. So as Pavan, Kaushik and Aniruddha are suggesting, it will be of type node, and that can be a problematic if we write the code like this, node star and then next, and it appears that both next and x are of type node star. So this is just a convention, it has nothing to do with the correctness, and therefore I have written it like this. Yeah, this is not a silly question, Pavan. I think we should ask these questions. Our goal is to learn. You should be able to understand everything that I am saying. Okay. Any other concerns, questions? Feel free to ask. All right. So, assuming that we have understood this class list, at least the API, now we can, instead of getting into functions, I am going to first show you main. Main should look very similar to what we do in C, just that I am going to define a variable of type list. List L is going to give me that. Mayank is asking, how can we make it a generic data type? We'll have to use templates there, and that is not really going to, I'm not going to cover that, but essentially that will mean that you can do something like this. Template class T or type T, and then that node of T, and then this one I can do template class T, and here I can give them T. So then it becomes like whatever you are passing, that becomes the type. Many of you might have used vector of int, right? So that int is essentially the type going to the templatized definition of the vector class. So in a similar manner, you can have the node definition or the list. In fact, yeah, you will need that. So you will need the templatized. So you can say something like list int L or list char L2, and all of this is possible if we do it in this manner. Some of the functions will also need to change depending upon the type, but otherwise most of it will remain the same. Right? Again, templates is not something which we are going to do in this course, so I'll not get into that. But if you are interested, some of my slides on object-oriented programming are available on my other teaching web page. So feel free to go through that. That might be useful. Okay. Any other concerns, questions? All right. So then the functions remain very similar, right? Since our type is char, therefore I am inserting A, B, and so on. Then I'm printing the list, finding A recursively, and so on. So these are just calling of different functions inside that list. Okay, and finally I return C. The exact definitions of functions I think we will do maybe in the next class, but I just try to compile this whether it works. Sorry, we'll have to use G++, and it works fine. Like we said, whether we have node or class node, it should be okay. Similarly, you can define this as struct, and that should also be okay. Right, so it compiles fine. And if I try to run it, then it gives some output. We can check if that output is correct and so on. But more importantly, just one small part, in main we never called the constructor. As you can see, this is list L, and then I'm just inserting A. Right? So if I comment this out, then the constructor should get called, which should create the empty list. And in the constructor of that, I have actually written this statement. This is a constructor. I'll tell you about the syntax in the next class. But this function should get called because I'm creating the list, and therefore I should see this getting printed. Right? So empty list created is getting printed, which means that this constructor was called automatically whenever I declared a variable of that type, in this case. Okay. Okay, so my discussion ends here. I'll take up questions. If you have classes, please feel free to go ahead. If we don't define the constructor explicitly, is there any default constructor? Yes, there is a default constructor by default, but it is not going to do anything, so don't rely on it. Yes, there is a default constructor which C++ provides. Kaushik is asking, within struct also we can have private declaration rate. The struct and class are synonymous in C++, except that the default visibility in struct is public, default visibility in class is private. Otherwise, there is no distinction between these two in C++. So you can do everything with struct also. Mayank is asking, where are these abstract functions implemented in our code? These are implemented between main and class list. These are all implemented. Don't worry. I'm going to go over all of this. I just skipped this and went to the end of the file. We are going to discuss all of this in the next class. But this can also be moved to a separate implementation file. That is also okay. Then there is a question by Aniruddha. Even if we comment out the other functions, the constructor will print that statement. Yes, that is correct, and that's what we saw. Why do we even have struct if class can do everything the struct can? Because C++ was supposed to be a superset of C, right? So it had to do a kind of backwards compatibility. So it had to support struct, but it also wanted to support new functionalities, and therefore it added all this. So this again, it's the G++ implementation which is having this synonymity between struct and class. But there could be other implementations which might not support structs having functions, for example. Right? So it's the GCC version which is providing this. Sunil Kumar is asking, should we specify constructor outside the class only? No, you can specify it inside the class also. And I'll also explain that. But this is a good programming practice. Therefore, I have moved it outside. And so that your interface remains separate. Right? So your class, like we have defined the function here, right? Whereas we have not defined any of the functions here. So if it is a very small function, then it's okay to define it right there. But in general, you should separate the interface from the implementation. And that is what I wanted you to kind of indirectly learn out of this. But otherwise, it is supported. You can have the implementation here also. Saicharan is asking, to avoid reallocation, can we store elements in an array? And when the size is exceeded, make a new array and make the old array point to the new one and continue inserting instead of okay. So array pointing to the new one is a possibility. So essentially, you will have a linked list of arrays, right? So the single element, the node will not contain a single element, it will contain a bunch of elements, right? And then there is a linked list of these arrays which you can create. Yes, that is also a possibility. Some implementations do take advantage of such a thing. Not the standard ones I know, but definitely this is a useful data structure. Good thought, Saicharan. Any other concerns? Alrighty, so we'll stop here, and I think our class is now directly on Tuesday, I think. Yeah, there is a question from Andrea. Could you repeat the NodeStarNext versus StarNext? Sure. Okay, so let me, sorry. Right, so these are the two variables of type NodeStar is what we will think it is, but that is not how it is. It just means that that star is associated only with next. and previous is of type only node and not node star. Right? So this space is immaterial. Space doesn't cause any problem. It's just that it is our perception, and therefore to avoid that perception, I declare it as node space star next, so that it is clear that previous is of type node, not node star. Any other concerns? Surya Narayan is asking, can you explain linked list of arrays? How will the last element of old array point to? No, no, no. So, okay, I'll explain that. So, it's not that the array is going to point to the next element. It's just that you will have to maintain an array and then a pointer. So, the pointer is going to be separate from the array, very similar to our implementation. So, here, if I say data type of n and I get rid of the previous, then I have an array and then there is a next pointer. So now instead of storing one character, you can store large set of characters. And then there is a linked list pointer which is pointing to the next one. The next node will also have an array of characters and then a next pointer. So that's what we were seeing, not the array. You can possibly do some jugglery using typecasting such that maybe the last 4 characters can point to the next pointer and so on. That is also possible, but I think this is much cleaner. Kaushik is asking, what if we do not have the list constructor? By default, would anything happen? By default, nothing will happen. There is a notion of a default constructor which does nothing. So it's not that all your array elements are going to, or your pointers, etc., will get initialized to null. That may not happen. So don't rely on a default constructor. Are the codes available for us to view later? Yes, all these codes are available on the course web page, and those will remain on the course web page. You can refer to it anytime, and you should refer to all of these codes for your placements, whatever, for your assignments, etc. All of these are available on the course web page, and since I have shared the screen, I think I can just show you. Oops, I think. This is your course web page, right? So there you have all these codes available here. So basic codes in C++ are there, and then all of these maximum sequence sum, then this linked list implementation, this sll.cpp is what I have opened. Mani is asking, is next is pointer in the node class? Yes. And that is why it's called a self-referential structure. It is referencing itself, right? Or at least the type is going to be the same as the node, and therefore it is called as a self-referential structure. All these linked lists, stacks, queues, etc., can be implemented and graphs, etc. BMChandana is next. Yeah, so that I think I have answered. Pointer to a node or pointer in the node class? Pointer to a node which is in the node class. Right? So in the code we have NodeStarNext is a pointer to node. Right? Star indicates that it is a pointer of type node, and it is inside the node class. Right? That is how we have defined this to be. Right? So you have this node which has the character as well as the pointer, and that pointer is pointing to the next. Aniruddha is asking, each time a new object is created, constructor is called, and so it will print that statement, right? Yes, that is right. So if I have list L2, then it should print, oops, I think I made some mistake. N was not declared, okay. I have not changed the definition. Right, so it will get called twice. One for L, another for L2. Any other
Sir, do you have some time? I have one doubt regarding complex.
Sure, you will extend my lunch, but that is okay. Go ahead.
So let's say we have to make a linked list of elements 1, 2, 3, 4, and the order must be preserved, and we are feeding in the values in the same order 1, 2, 3, 4. So like the values should be added at the end of the list. So the total complexity will be here like 1 plus 2 plus 3. So n into n minus 1 by 2, right?
That is correct.
It will be
Yes,
O n square, right?
that is correct. So when we say the complexity is order n, we talk about the complexity of one operation.
Yeah.
So yeah, but the complexity in your case, if you have n inserts, is going to be n square. If you have k inserts, it will be k into n.
Okay. Yeah. But the assignment, it like there's a restriction of complexity between O m into n. So that's what I was wondering about.
O m into n. Yeah, so O m into n for the whole matrix for one operation, not the all the operations. For one operation, the complexity should be m into n.
Okay. Yeah.
The number of elements is m into n, and therefore you will have to traverse it from left as well as from the top, and therefore the complexity will become m into n.
So, but making one row itself will take n square, right? So if there are n rows, sorry, n
No,
columns.
yeah, that is correct, but for one particular element, right? So if you have to insert it in mth row, you have to traverse m links and then reach the row, and then you have to traverse the across that list. So why is it is it m into n or m plus n?
I think so. It's m. I could be wrong. M
In
into
my
n.
okay, if it is for one operation, it should be m plus n. If it is
No,
given
it's for
for all
creation
the,
of matrix, entire creation.
oh, I see, I see. That is okay because that complexity will come into play as you are inserting. So it will be m into, okay, will it be m into n?
It should be m into n square, right? So because for making every row, it will take n square, right? Or is there any shorter?
Yeah,
I think
so
there's some.
we said that the insertion can be done in order one time if you maintain some additional information, right?
But here we should use, I think, only the single linked list, I guess, and no
Yes,
tail also.
well, that is not given. I mean,
Okay.
I don't think it is given that you should not use it,
Okay.
right? Okay. Saicharan is asking if I am writing a code with order n square time complexity, is there a way to know if a lower time complexity is possible or not? Okay. This is a very difficult question. So there are some algorithms which have a lower bound. Sorry, not algorithms. There are some problems which have lower bound, which means that you cannot solve that problem in time lower than that. These lower bound arguments are little difficult and not always are available. For example, there might be some problem for which an order n square algorithm might exist. That is the best known algorithm. But nobody knows if it can be done in less than n square time. So there are some problems for which this is known, for which it is okay. But otherwise, if you don't know the lower bound, then it is all in the air. We can't say anything. Unless somebody comes up with an argument that the complexity cannot be better than this or the lower bound is this and so on. It's not possible.
Sir, so while practicing problems or something like, how do we find out like what we've written is right? Is it about being smarter?
It is also about being smart, but smartness is more about the absolute performance. I think the algorithmic complexity that we are talking about requires the knowledge of the problem and, of course, the algorithmic techniques that we use to solve that problem. For example, we say that sorting is order n log n. Now, somebody might say that no, I can, if I think enough, if I bring in enough smart people, then maybe I can solve it in less than n log n time. But there is a lower bound on sorting that it is n log n, which means that you cannot do better than that if we are using a comparison based sorting. Then irrespective of the smartness of people, they won't be able to prove it, right? So as far as the practical aspects are concerned, there we do require smartness, and that will reduce sometimes only the absolute time. That might not reduce complexity, but it will probably perform much better than the original.
Okay, but what I mean is like, so the sorting I've learned is like bubble sort and selection sort. They can be done only using n square complexity. So
Correct.
then, until you mentioned, I didn't know that it can be done with n log n time complexity.
Otherwise,
So
okay.
something like that.
Yeah, for that, the problem is sorting. The problem will have a lower bound. And that is the reason why it becomes a little challenging, because now earlier you could have talked about a particular algorithm, that the complexity of this algorithm is so and so. But now you are talking about irrespective of what algorithm you use, the complexity cannot be better than or lower than this. So the lower bound arguments become a little difficult. So if it is available for the problem, well and good. But otherwise, there is no, I mean, there are techniques to model the lower bound, which I am not fully aware of. But in general, it is not known for many problems.
Okay, sir. Okay, thank you.
Any other concerns? Okay, I'm assuming that you guys are also hungry. We can stop here. Okay, so I'll stop the recording now. See you in the next class. Bye.